Hello, welcome to your lesson on basic rules of derivatives. If you haven't watched the first video on what is a derivative yet, make sure you go back and watch that one first. But here, we're going to go back and review just a couple key things about derivatives. First, we're going to go online and check this out. When we were talking about derivatives, we were saying that derivative represents the slope of a curve. So the derivative function was actually called the gradient function. So check it out. When we want to know the slope along the curve, what we do is we pick a point and we say at that point there is a specific slope. And the slope at that point is represented by a tangent line connected to the curve. And now as we move that point along the curve, notice the tangent line changes. The angle of it changes. That means there's different slopes as you proceed along a curve, and that makes sense because as we go we can see now negative slope, now steeper negative slope, now almost zero slope, and then positive slope. Okay, so the slope changes as you follow a curve, and that slope is represented by a tangent line at every one of those points. Okay, that's where derivatives come into play. We also did an investigation with a parabola, y equals x squared, and we checked what is the slope at each of these points here. And the slope can be represented again by the tangent line. So we looked at this tangent line and we found that slope to be -4. And then we looked at this tangent line here and we found that slope to be -2. And then we looked at this tangent line and the slope was 0. Then we looked at this tangent line, the slope was 2. And finally we looked at this tangent line and the slope was 4. So notice as we go along different x values along the curve, we have different slopes. However, those slopes have a pattern, and the pattern it was 2x here, that 2 times these values gave these values. Therefore we said the gradient, the slope, can be found using this function here. So this function is called a gradient function, and it is the derivative of this original function. So here's the original, here's the gradient function, this is the derivative, and the derivative function is the gradient function. So the derivative is the gradient function. Okay, that's a key point. I think we've really hammered that point home, so I hope you understand that now. Alright, we finally recapped by saying derivatives have different kinds of notation. So if we have an original function here, here is our derivative of y, and that 2x we found was the derivative of that function. And you can write derivative like this as well, or you can write derivative like this if we began with an f of x functional notation. Alright, let's keep going. So, the derivative gives the slope of the tangent line. So here's a curve, here's a tangent line, the derivative gives us the slope. Let's continue with that idea. So now let's move on to basic rules of derivatives. So let's say you're given these functions here. Alright, y equals 3, y equals -5, y equals 8, y equals -10. And we have two questions. What is the gradient of y equals c? So imagine these are all the same form, right? Y equals some number. So it's asking, if you have an equation that y equals some number, what's the gradient? Well, let's remind ourselves what these graphs look like. I have them here. I think I have them here. There they are. There's y equals 8. There's y equals 3. There's y equals -5. All these lines, anytime you have y equals something like that, just a number, they are horizontal lines. So what's the gradient of those lines? Well, clearly the gradient of lines of that form, or in other words, when y equals c, some number, the gradient is 0. There's no slope here, so the gradient is 0. Okay, so what is the derivative of y equals c? Well, we know the derivative gives the gradient, right? So that means the derivative, therefore, the derivative of y equals c, the derivative must be 0. Because the derivative gives a slope, and these equations or these functions always have a slope of 0 no matter where you go on them. So the derivative of this kind of function must be 0. Important to know, remember that. Okay, let's try another one. Now we have lines that are a little bit more complicated, not as simple. Okay, y equals 3x, y equals -7x, y equals 4x, y equals x. These lines now have an x in them. So what do those look like? Let's take a look at those graphs. Okay, here's y equals x. This red one is y equals -7x. The light blue one is y equals 4x. And the black one is y equals 3x. So these are simple lines that all pass through the origin. So they have a y-intercept of 0. But that number in front there is what? That number in front of the x is our slope, right? These lines all have a different slope. So what is the gradient of y equals mx? Let's say we said these are written in a general form like this with m written here instead of these numbers. So what would be this gradient of those? Well, the gradient of those is m, right? These equations are written in y equals mx form, and then we know that number in front of x is the slope. So when somebody says, what is the slope? Well, the slope is m, right? That number there represents the slope. So now, what is the derivative of that function? And again, remember, derivative represents the slope. So if we have a line y equals mx, therefore the derivative must be m. Alright, because the derivative of the slope, and each of these lines has a constant slope. So if somebody said, what's the slope of this line? You would say it is just whatever number that number is. So the derivative is that number. Alright, we'll see how we're going to use this in a moment. Okay, so now let's recap some things, and this is a key slide here. Let's work carefully on this. So when we had an equation like this, which is a horizontal line, what was the gradient function? Well, a horizontal line has no slope, so the gradient function, the derivative, is 0. Okay, next, when we have a line now like this, remember this is like the one where it has a slope. This is the slope, mx, this is mx, this is the slope. So what's the gradient function of that? In other words, what's the slope of this one? Well, the gradient, the derivative, is 2, because this one always has a slope of 2. Okay, but now things are going to change a little bit. Remember we did the experiment on or the investigation into y equals x squared? That's a parabola. That one does not have a constant slope like these two had. This one had a constant slope of 0. This one had a constant slope of 2, but a parabola doesn't have a constant slope. The slope of a parabola changes. So what's the gradient function? Well, do you remember what it was when we figured it out in the investigation? Well, that gradient function was 2x. So the derivative of this is 2x. And this gives the slope at any location along the parabola. So here the slopes are always the same, right? It doesn't matter what x is. This is always 0, this is always 2. But now, as x changes, this slope changes because you put different values of x in here. And that makes sense because we have different slopes along a parabola. Okay, next. What do you think that the gradient function of this is? And now I want you to consider this one and this one. Do you see maybe in your head kind of what happened from this to this? Okay, there's a simple rule that takes us from here to here. So apply what you think happened here to this one. What do you think the gradient function is? Maybe you came up with this. So maybe now you're seeing what the rule is. I can see this exponent kind of dropped to the front here, and then this exponent was reduced by 1. So the 2 goes in front, and then this 2 minus 1 is 1, and this is x to the 1. So over here, this 2 dropped to the front, multiplied that 2, and this exponent was reduced by 1 also. Interesting, that's the rule, it looks like. Okay, so try this one. What would be the gradient function of this one? In other words, what would be the derivative? Well, it would be 6x. Maybe you saw that rule in action again. The 2 drops to the front, multiplies the 3, becomes a 6. And then that exponent is reduced by 1, so we just have x. Okay, next one. How about this one? I think you're getting the hang of it now, I hope. The derivative of that, or the gradient function, is 3x squared. Notice the 3 dropped to the front, and then this exponent was reduced by 1, which means now it's 2. Okay, try this. Now that you've seen those, you can write a general rule. What happens when you have something x to some power? What is the gradient of that? What could be a rule you could write using just x and n here? Alright? Alrighty, let's see if you came up with this. Here is our general rule. When we take the derivative of this, we drop the exponent, so n goes in front, and then we reduce the exponent by 1. Okay, let's try this with this now again. So we have 2x cubed. What should the derivative be? What is the gradient function? It is this. Okay, next one. We have this. I see an a now. Okay, so what's going to happen here? What's the gradient function? What's the derivative? It is this, 3 times that a value, right? Okay, now we're back to another general rule. So a little more complex than just x to the n. We have ax to the n. So what would you write as your general rule for the derivative of that using a and n? And here's what we have there, right? The exponent drops down, multiplies the a, and then you reduce the exponent by 1. You have learned the most basic rule of derivatives. It's a very important one. It's called the power rule. So now just a reminder, derivative is the gradient function. So if we have this, then the derivative is this. That's the rule we just came up with. Here's an example of that. Here's a function. Here is the derivative. The 5 multiplied by 7, 35, and this was reduced by 1. Great, try another one. The derivative of that is this. Check your work. Alright, now if we have a function that's bigger like this, look, there's so many more things going on there. This is called a polynomial. Well, the derivative would just be the power rule that we learned applied to each part here in order. So take a look at these together, compare them. Okay, and now let's try one like that. Let's see. So here we have this. So you're just going to apply the rule we just learned to each term here. Alright? Here's the answer for that. Here's the derivative. This 4 dropped down here. This became 8. Then this reduced by 1. Then this, let's go back. Then this 2 multiplied by this negative 5 to get negative 10. And then this reduced by 1. Now it's x. Now we know when there's just 7x, it becomes just 7. Okay, when there's just x to the 1 power, it just remains as a 7. And then when we have a constant, no x, there's nothing. The derivative of that is 0, so it's gone. Okay, memorize this rule and how it works. Let's try some examples. Okay, I'm going to help you with the first one, then you'll try some on your own. So here's the first one, number 1. Here's our function. We take the derivative of that. The derivative is y primed equals 12x cubed. The 4 dropped down, multiplied to 3 to make 12, and then the exponent reduced by 1. Now the next part of this question says, find the gradient of the tangent when x equals 2. So remember, this is called the gradient function. It allows us to find the gradient or slope at any point. So when x equals 2, we're going to put 2 in here and see what we get. When we put 2 in here, 2 cubed is 8. Times 12 is 96. So when x equals 2, y primed equals 96. And that tells us the slope of this function when x equals 2 is 96. It tells us the slope when x equals 2 of this function. Alright, try the next one, this one here. Okay, great, check your work. Here's the derivative. I'm using the different notation, and this is the slope at x equals 2. Next one, try this one here. Here is our derivative. Again, I'm using this notation now. And then when x equals 2, the slope is 11. Next one, try this one. Here's the derivative. And now the slope when x equals 2 is 14. Notice when we use f of x notation, it makes things easier. We don't have to write this out again. When x equals 2, blah, blah, blah. We can just say like this. When x equals 2, we just put it into the derivative function. So f primed of 2 equals 14. And again, that tells us on this original function, if we graphed it and we went to the point x equals 2, this would be the slope of the tangent line at that point. Okay, this next one's a little different. Let me help you out. Here's our function. This one here. We have 2 over x. Whenever you have a fraction like that, you have to change it before you take the derivative. You may remember the rule when you bring something up from an exponent, from the denominator and you bring it up, that x has a power of 1. But when we bring it up to here, to the numerator, we make it a negative 1 power. Now we can take a derivative of that. Here's how we do it. You follow the same rule. That negative 1 drops to the front. Negative 1 times 2 is negative 2. This becomes negative 2 because we reduce the exponent by 1. We subtract 1 from it, becomes negative 2. And then plus 1 because the derivative of x is just 1. It is the derivative of something with x to the 1 is just the number in front, and there's a 1 here that we don't see. Alright, that derivative can be written further like this. That negative 2 again, we know when there's a negative exponent we can drop it to the denominator like this. And now put x equals 2 in there, and we get 1/2. Check your work on that. Now try this one. It's a similar kind of problem. And check your work on this one. Again, that was brought up like this. Therefore, the derivative is this. The negative 2 is dropped down to make negative 6, and then reduce the exponent by 1. Now that derivative can be rewritten like this because we have a negative exponent, so it can go back down to the denominator. And now put x equals 2 in there, and you get